Hi everyone, this is our new lecture on, on special chapters of higher mathematics. This time we're going to talk about some elements of games theory. So this games theory, what it's all about. Do not get misled by this term, games theory. It's always about decision making. This games theory is actually about making decisions in different conditions. So today we're going to consider this topic, decision making, while not accounting for probabilities of possible states of nature. So we'll consider some factors that cannot be controlled and how to make decisions while we don't account for probabilities of different possible states of nature. So we need to consider different factors that cannot be controlled, but these factors can affect our decisions because we make a decisions in conditions when we don't know everything about the nature, about the environment we're dealing with. So when solving real life tasks, we have to deal with nature. We have to deal with nature. The nature is gonna influence the way we choose to accomplish our task. These ways used to accomplish the task are called strategies. So we need to define our strategies depending on the uncertainties. So when we plan our strategy, we need to account for different factors that can help or hamper the goal achievement. These factors may include weather, business climate, demand for certain goods on the market, time necessary for maintaining and servicing some equipment, and so on. So this games theory is used basically in economy and management, and this is so we consider this as a mathematical framework for making decisions. The common characteristic of all these factors is that they're beyond any influence, so we don't control them, or we don't control, it's not under control of any individual or group of individuals. So we need to analyze these factors. There are three big groups. These factors can be categorized in these three groups: fixed or known, random, and uncertain. Now we talk about differences. Fixed factors, they can be considered as non-random, but just unknowns. That some values of factors are unknown. For example, throughput of equipment, distance between sources and destinations, resource demand per certain time. So this can be accounted for in quite straightforward manner. Random factors are represented by random variables with known distributions. This is the key for the random factors. So we can use the framework of statistical theory and probability theory and statistics to deal with these random variables with known distributions. This means that if some factor denoted as y can take certain set of values, then the probability of every value is known to the person responsible for decision making. For example, it takes this particular state or value with certain probability and every other with a known probability. So we can account for these different states of or different values with certain probabilities. Sometimes these random factors can have continuous distribution or discrete distribution, so I'm not gonna stay and focus on this slide for too much time. Uncertain factors. The difference between random factors and uncertain factors is that For uncertainties, we don't have a probability distribution. We only know a class of distribution. We can only know a class of distribution. For example of deterministic uncertainty. Temperature in Kharkiv on June 21st never gets below +10 and never goes beyond +35. So this temperature represents an uncertainty with a range of possible values from 10 to 35 Celsius, degrees Celsius. So, but there's no distribution. There's only the range. And we don't know the probabilities within this particular range. So this can be called an uncertainty, an uncertain factor. We can add some belief and express our uncertainties in terms of beliefs. So sometimes we can rely on objective knowledge in form of distribution, or in form of odds, express our odds or our degree of belief in form of odds. So the first probability is objective characteristic. The odds is our subjective knowledge, is based on our belief on something. Like we believe that this outcome will be more probable than the other. It cannot be based on some objective knowledge, but we can know from previous experiences or from some other sources that this is true, so we can deal with this. But we deal this with as uncertainty, not as objective knowledge. Uncertain factors can be expressed, for example, or explained by this particular example. A decision maker has information that payoff value generated by selling some goods can take two values, C sub 1 and C sub 2, with probabilities ranging from, for C sub 1, ranging from 0.3 to 0.5. And the value of C sub 2 can be taken with probability ranging from 0.6 to 0.8. The distributions are unknown. It should be noted that uncertain factors can be related to actions of other stakeholders in the operation who can pursue their own goals. So there are different kinds of games, but here we consider only games against a game with nature, and I'll explain the difference in a bit. Possible decision making. So how do we actually make decisions? Decision making is not in known condition. That's the first option. Only fixed uncontrollable factors are present. Second, decision making in conditions of risk. So this risk presumes that only random uncontrollable factors with known distributions are present. And third option, decision making in conditions of uncertainties. As the name implies, uncontrollable factors include some uncertainties. So, how can we deal with all these factors? So, here we consider the so-called non-probabilistic decision making, when the stakeholders involved in the process don't have any antagonism. No one opposes one another. Then such situations are called games with nature. So the nature doesn't play against us. All uncertainties and unknowns depend not on adversary who deliberates his actions, but on the nature itself. So the nature doesn't play deliberately against you. But if you disregard the risks involved with the nature, you can find yourself in troubles. But you can deal with the nature, right? Again, by nature we understand any objective conditions in which the decision once made is to be turned into some actions. So, by nature we understand someone who doesn't deliberately play against us. Because when you play against some opponent, the opponent plays deliberately and deliberates his actions against you. So, in It's in a situation like this, when no party is playing against you, the first party is to make a decision. So you, as a decision maker, are making a decision, and the other party, the nature, doesn't take deliberate actions to oppose the decision in response to the decision, to your decision. Yet its actual reaction is still unknown. So you have to decide whether to take your raincoat with you tomorrow to school or not. It depends on the rain. Will be will there be a rain tomorrow, or there will be no rain, right? So that's your decision. If you have your raincoat with you and there is no rain, you're still safe, but you're bringing an extra weight with you. But if you don't take your raincoat but there's rain, you're in trouble. You get wet. So this is how it works. You make decisions against in conditions of uncertainty. Let's consider this example. This example is from business, and it's a simplification, but it shows all the basic elements of games theory. It all boils down to the so-called payoff matrix. Payoff matrix. We'll explain on that in a while. But first, let's consider this example. Vista marketing department reports the expected sales of software produced by the company depending on three variants of pricing policy. So the company can decide on the price per unit product. It can be, for example, $8 per unit, 8.6 per unit, or 8.8 per unit. But the price affects the sales. So, and sales depend not on the price only, but it depends on the market conditions. So, this department, the marketing department, does some research regarding the market conditions and comes up with some numbers. For example, in case of best market conditions, the company may sold 16,000 units of this particular software at price of $8 per unit. But it can sell only 14,000 units at the price, if the company sets the price as at 8.6, and it can sell only 12,500 units if the price is set to 0.8. But that's only if the market conditions are the best. So the market is in favor of this particular product. But market cannot be the best. It can be mostly probable market conditions, like average market conditions. So given the most probable market conditions or mild market conditions, at the price of $8 per unit, the company may sell only 14,000 units of this software. At the second price option, 8.6, it can sell 12,500, and only 12,000 at $8.8 per unit. But if the market turns worst, to be in worst conditions, the sales can drop to 10,000 at the price of $8 per unit, to 8,000 at the price of 8.6, and only to 6,000 units at the price of $8.8 per unit. Plus, the company has some fixed expenses of $40,000 per year. These fixed expenses are related with some production and technological processes, like you have to pay some salaries and some fees, some shipments, and so forth. And there are direct expenses of $4.0 per unit. For example, you have to copy them on some material medium, so there is an expense, the direct expense of $4 per unit. So we can turn or represent all this data plus these expenses in form of payoff matrix, the so-called payoff matrix. So we can express this in terms of payoff per year. Payoff per unit, it's $4. So the unit price, the payoff, it's actually the profit. So it's the price minus direct expenses of 4,000 of $4 per unit. So the payoff is price minus direct expenses. So it's only 4. So when you calculate the payoff at the price per unit, and this is the payoff, possible payoff by selling 16,000 units of this particular software. So you just multiply it by the price or by the payoff per unit and subtract the direct losses, the direct expenses per year. So we get these numbers. We get these numbers. So at the payoff of $4 per unit, given the best market conditions, the company may obtain the payoff of $24,000 by selling these 16,000 units of software. At the second price option, the payoff per unit will be 4.6, and given the best market condition, the company may obtain the payoff of $24,400 by selling 14,000 units of software, and so forth. So this is our payoff matrix. This is our payoff matrix given best market conditions, mostly probable market conditions, and worst market conditions. We note that at the price option of 8, when the payoff is only $4 per unit, the company may not be making money if the market turns to its worst conditions, and the company may actually lose money if it sets the price to a higher value of 8.6. So the payoff will be per unit will be 4.6, and the company will be losing money instead of making money if the market turns mild or very good. Instead of making money, the company may start losing money. Or even if the company sets the price even higher or expect the payoff of $4.8 per unit and the market turns to its worst conditions, the company may lose quite a great deal of money. So how do we make, or how does the company make a decision? How to account all this, how to account for all this information to make a decision? Decision is really simple. Which pricing option is to be chosen? Which price is to set for the company, given that there is some uncertainty regarding the market? So let's discuss this a little bit. For example, if the market turns to be the most probable, then the highest payoff is 17,1600 if the price is set to the highest possible value. However, the price of 8.6 with a payoff of 4.6 per unit can be a more preferable than 8.8 for the company. Expected payoff for the most probable market would be slightly lower if the market turns to the to be mild, then the company will receive slightly less revenue from selling this software. But if the market turns to be the best, the payoff will be a little bit higher. The payoff will be higher even at this price option. And if the market turns to be worse, the losses will be less than in previous case. Yet the price of $8 per unit is the only price that will not generate losses for the company if the market turns worst. So obviously, if the market turns worst, this is the only pricing option which will not generate losses. The company will stay as it is, without making money and without losing money. So, we actually can analyze different price options and make a decision. How do we do this? So the problem is which strategy, which in our case is the price, is to be adopted. One of the key factors in such kind of problems is nature or external environment, which can be in one of its possible states. For example, in our case, it's best, probable, worst. So we denote these states of nature by these S capitals. S sub 1, state of nature, which is the best. S sub 2, which is our probable. S sub 3, and so forth. There can be several states of nature. In our previous example, there were only 3 states of nature. So the decision maker can adopt various strategies. Pricing policy. We denote these pricing policies as strategies. A sub 1, A sub 2, A sub m. A sub 1, A sub 2, A sub n. So we denote states of nature as S capitals, and we denote the strategies by A sub 1, A sub 2, A sub 3, and so forth. So the mathematical formalism looks like this. The payoff can be regarded as usefulness, F sub ij of every strategy A sub I, given the state of nature S sub j, which brings us to the matrix. So formally, mathematically speaking, we've got this payoff matrix with elements F sub aj equal to usefulness or payoff depending on strategy and states of nature, where these subscripts I runs through all the strategies available, and states of nature runs through all different states of nature that we know of. Formally, this matrix can be designated as L capital. So, let's consider the possible ways to address the decision-making problem given the conditions stated above. These ways can be split into 2 big groups. Decision-making that doesn't take into account the information on probabilities of the state of the nature being in one of its possible states. So, decision-making in conditions of uncertainty. We don't know the probabilities. We just know that there is uncertainty regarding in which state the nature will be at the time we'll execute our decision. And the second way, or the second group, is decision making that does take into account the information on probabilities of the nature being in one of its possible states. Decision making in conditions of risk. So we know the probabilities, but we have risks. Here we consider the first group, decision making in conditions of uncertainty. We don't know the probabilities. So let's consider a game with nature. We have a payoff matrix. Formally, we're given a payoff matrix. Here S sub 1, S sub 2, S sub 3 are different states of nature, regardless of what they are, what do they do, how do they influence our decision, and so forth. They just are different states of nature. And different strategies available to decision maker. And given the combinations of every strategy, we have a matrix of all payoffs possible. So, for example, given that the decision maker adopts this option A sub 1, he can obtain different payoffs of 20 if the nature will turn in its state S sub 1. The payoff of 30 something can be, again, it's just numbers, relative numbers. 30 if the nature turns up in its state S sub 2, or 15 if the nature turns up to be in its state S sub 3. So all other decision-making options, which we call strategies, involve different kinds of payoffs. So formally speaking, this decision-making procedure boils down to analyzing this payoff matrix or different payoff matrices. So basically it's as simple as that. We just analyze this matrix and find the best option. Now let's consider this maximin rule, which is the rule to avert any risk. So to pick by risk aversion, we mean that we find the option, the decision, which minimizes the risk. This rule allows to choose the decision which guarantees the maximum payoff, given the worst state of nature. So we maximize our payoff given the worst conditions. So how do we do this? We find the minimum payoff. For all the decision-making options given different states of nature. For example, we analyze the first decision-making options, option A sub 1. The minimum payoff here is 15. This payoff can be obtained if the nature turns up to be in its state S sub 3. So for this particular option, A sub 1, this is the minimum payoff. For the second decision-making option, the minimum payoff is 20. It can be obtained if the nature turns up to be in its state S sub 2. This option has two different options, so it's either 25 or 25. So this is the minimum. And for the decision-making option A sub 4, the minimum payoff is 5. Again, it's for the state of nature S sub 2, whatever that is. So now we analyze. We have minimum of 15, 20, 25, and 5. And now we maximize this minimum. Find the maximum of these minima. Obviously it's 25, right? Minimum here is 15, but this minimum here is greater than this 15. This minimum here for this option is 25. It's greater than this, and it's obviously greater than this minimum. So according to this maximin rule or risk aversion rule, the decision-making option A sub 3 should be adopted. So regardless of the state of nature, we're going to obtain the minimum guaranteed payoff of 25. If the nature turns better, then we may obtain better payoff of 80. But in the worst case scenario, we still get our payoff of 25. So this is how we avert the risk. If we take another option, for example this, we may end up with this payoff, or sometimes end up with some losses. Instead of making money, we'll be losing money. But if the nature will be in favor, we can get higher payoff. But this state of nature is not guaranteed. We're still dealing with this uncertainty. We're not certain in which state of nature we'll find ourselves. So we need to pick these options, decision making options, by analyzing different risks. So this is one of the possible approaches to solve this task, solve this problem. So maximum rule, we avert any risk. We find the minimum payoff for every option and maximize this minima. So this is how it's done. So basically it boils down to this. We find this minima and maximize it. So obviously this is our solution. This is our solution. The strategy A sub 3 is optimal according to this rule. But there are other rules. Not necessarily this is the only rule to make a decision. Maximax, there's a risk-taker approach. This is another extreme approach. Instead of averting risk, any risk possible, we can take the risk in hope to maximize our payoff, to maximize our profit. So the opposite of this complete risk aversion is the risk taking, which can be expressed as maximax rule. Again, we have the same payoff matrix with the same states of nature, with the same 4 decision-making options. So our maximax approach is like this. We find the maximum payoff for every decision-making option, for every option. So it's 30 for the A sub 1 decision option, it's 75 for A sub 2, it's 80 for A sub 3, it's 85 for A sub 4. So we find all these maxima and pick the maximum of these maxima. So obviously if we want, or if we're ready to take some risks, we may find ourselves in a situation when we get indeed this maximum payoff of 85. But if the market or nature is not in favor, we may actually reduce our payoff like considerably, and instead of 85 we just get 5 or 45 depending on the state of nature. So by this particular risk taker strategy or approach to decision making, the option A sub 4 is optimal. Again, there's not there are other options how to decide upon optimum decision. Let's consider this. Our risk aversion approach is very pessimistic. The pessimism of maximum rule can sometimes prevent good opportunities. Prevent some good opportunities. But it's not the best option to remedy the pessimism by turning to the opposite approach. It also can be used, it also true in life. Like you don't remedy your pessimism by turning to absolute optimism. So you still have to weigh your decisions. So both previous rules can be replaced by the minimax regret rule. Minimax regret rule. Let's consider this for a minute. The minimax regret rule approach is to minimize the worst case regret. Instead of minimizing the worst case payoff, we minimize the worst case regret. What's regret? The aim of this is to perform as closely as possible to the optimal course. Here the minimax criterion is applied to the regret. Not the original payoffs, but the regret. It's the difference of the payoffs, but not any difference. It's smartly found difference of payoffs. It's not as pessimistic as the ordinary Maximin approach. So, we can find this regret by subtracting payoff, current payoff from the matrix in the matrix from maximum payoff for every particular decision making option. So the regret will be considered as profit which could have been obtained but was not obtained. So instead of maximizing the worst case payoff, we maximize the worst case regret. So regret is obtained simply by subtracting current payoff from maximum payoff. So now we get back to example 2 and find the regret matrix by subtracting all the values in every column from the maximum value of that column. So, given state of nature S sub 1, the best payoff for all the decision options is 85. So now, if the nature turns up to be in this state S sub 1, the maximum payoff would be 85. So, but if we pick another decision option, we reduce our expected payoff by some difference. This difference is our regret. For example, if we go from 85 to 25, it's minus 60. We reduce our expected payoff by 60 units. By 60 units coming here. So regret from option A sub 4 to option A sub 3 is 60. So we subtract this particular value of payoff from this maximum value. So we get 60. Regret of 60. But if we pick the A sub 2 option instead of A4, we get regret of 10. So we reduce our expected payoff only by 10 points. By 10 points. So by coming from this 85 to this 75 payoff, we have the regret of 10. It's less regret than in previous case. So we can obtain this by just subtracting this 75 from 85. We get 10. We get 10. And regret here is 65. So we reduce our payoff of 85 to from 85 to 20. The regret is 65. In the same way, we find the regrets given different states of nature, other states of nature, S sub 2, S sub 3. So formally, we just find the maximum in every column and subtract every current value from this maximum. So we get the new matrix. We have 2 0 regrets or 3 0 regrets. Now we apply this minimax rule to find the worst case regret, to maximize or minimize the worst case regret, minimax regret. So we find maximum regret given every decision-making option, which is for the decision option A sub 1 it's 65. For the decision option A sub 2 it's 60. For the decision option A sub 3 it's 60. And for the decision option A sub 4 is 75. And find the minimum. So minimax regret. We minimize the maximum regret given every decision making option here. So what's the minimum of this maxima is 60. So we obviously see that according to this decision making rule there are two optimal options, A sub 2 and A sub 3. So the minimax regret rule tells us that there are two optimal strategies, namely A sub 2 and A sub 3, which gives us this minimum regret. So these are our optimal strategies. According to minimax regret rule, A sub 2 and A sub 3. With regard to this matrix, the minimax regret rule involves some risks. But with regard to matrix of regrets, it minimizes the worst case regret, the payoff that wasn't obtained. Therefore, it's risk-free. So this approach, this rule, lies somewhere in between risk aversion and risk taking. So it's more balanced approach. There are some other approaches, but we're not consider them. When do we employ these rules, or any of these rules, risk avert, risk taking, or minimax regret? We have no information about probabilities of various states of nature. We make decision only once. Every possible risk is to be averted. There are also other rules. So we conclude as this: sometimes the decisions are to be made in conditions where the states of nature can affect the goal achievement. This goal achievement is expressed in our payoffs. Possible states of nature can be characterized with unknowns and uncertainties. The difference between the two is in the information available about these states. Unknowns involve probabilistic distribution. Unknowns means that probabilistic distribution is known, so that the probabilities of every possible state of nature can be evaluated. Uncertainties, we know only class of distribution, so we can have only coarse estimates of probabilities. Decisions can be also made without accounting for the probabilities of various states of nature. In this case, the procedure is called the non-probabilistic decision making. We have these three different approaches. Maximin, we avert any possible risk. Maximax, we take, or we're ready to take some risks. And minimax regret rule. Risk, but we take some risk, but we do this cautiously. There are others. So, thanks for watching, and until next time, bye.